it seems that you are done now, Subir, about the talk.
Yes, I'm done. I'm done. Yes.
Okay, then let's move now to the next one. So are you ready now for the next talk, Benjamin?
Yeah. I'm ready. Should I share the screen?
Yeah, sure.
Okay.
Okay.
Do you see the screen?
Yeah.
And do you see my mouse?
Yeah, I can see
Okay,
it.
great. Yeah, I can go whenever.
Okay.
I think you can go ahead.
Yeah,
Oh,
okay.
I think,
okay.
I believe.
So
I don't know. Sorry, Mudahir should speak.
Yeah, no, I just said it, but maybe you didn't hear me. Yeah, go ahead.
oh,
please.
okay, great. Okay, thanks. Okay, thanks very much for the opportunity to speak here at this conference. So I'm going to talk about harmonic analysis of 2D CFTs. And this is based on a paper that just appeared a few weeks ago with my collaborators, Scott, Liam, Alex, and Eric. And let me first say some big picture motivation of the kind of question that we want to address in this talk. So we're going to be studying 2D CFTs in this talk. And there are many very good reasons that someone might be interested in 2D conformal field theories. You might be interested in critical phenomena in 2 dimensions. You might be interested in string theory and studying the world sheet string theory. You might be interested in studying quantum gravity in 3 dimensions in anti-de Sitter space. And there are other reasons you might be interested, including you might be interested for some just purely math reasons. And in 2 dimensions, these conformal field theories have a lot of interesting constraints that their higher dimensional cousins don't have. For example, they have some infinite dimensional Virasoro symmetry, and they have modular invariance. And the question I'm going to address in this talk is, can we constrain possible partition functions of these theories using these techniques? And in particular, we're going to be focusing on modular invariance. And I'll say more introduction about what this means. The outline of this talk is, first, I'm going to review this harmonic analysis. This is some new technology that we're going to be borrowing from the mathematicians, which will give us new ways to look at some of these constraints on 2D CFT partition functions. And then we're going to apply it to 2 different types of CFTs. First, as a warm-up, we're just going to be applying it to free bosons on some lattice. Then we'll do more generally 2D interacting conformal field theories, and we'll prove some general theorems that I don't know how to prove without this technology. And along the way, we'll talk about applications to things like holography and averaged holography and things like this. Again, just to emphasize, the main strategy we're going to be using is modular invariance of the torus partition function. So if we write the 1 loop partition function, z of tau here, the key player is that this is invariant under any large diffeomorphism of the torus, which is just the action of some group SL2Z. So in some sense, tau, this modular parameter tau, is not really valued in the upper half plane. So this is the complex numbers with positive imaginary part, but really this quotient H mod SL2Z. So that's a big picture overview of where we're going, and I'll say everything in more details. And of course, interrupt me at any time if you have questions. So let me start by reviewing what this fundamental domain of SL2Z is. So this is the group of 2x2 matrices with integer entries and determinant 1, and it has a natural action on some coordinate in the upper half plane. And if you look at a fundamental domain of this action, it turns out that it's this gray region over here, which extends off to infinity. Some conformal field theory's partition function is not really a function of the entire upper half plane, but only of this gray region. And this is an extremely constraining property. For example, maybe the most famous application is Cardy used this property to show that all CFTs have some universal entropy in the higher energy regime, which has some very beautiful interpretations as black hole entropy in the ADS CFT context. And there are many constraints that you get, because most functions you write down that are just functions of this upper half plane H will not restrict to this fundamental domain. This upper half plane has a natural metric given here, where x and y are the real and imaginary parts of this modular parameter tau. And with this metric, we can define a Laplacian. Where we're going is we're going to be expanding all modular invariant functions into eigenfunctions of this Laplacian. So it's just like doing quantum mechanics, where this is the energy operator, and we're expanding in energy eigenfunctions. Once we have this basis, there's also a very natural inner product you can define, which is just defined via this basis of eigenfunctions. And the inner product can be defined just as we do as we learned in quantum mechanics, using some inner product where we integrate. Now the measure has this y² factor, but we just integrate the product of the two functions, and we take the complex conjugate of one of them. And so this inner product will allow us to read off the basis coefficients when we decompose into eigenfunctions of this Laplacian. So the idea is the following. Just like in Fourier analysis, we're going to decompose square integrable modular functions into eigenfunctions of the Laplacian on the arbor half plane. So now, for a little bit, I'm going to just tell you some math facts that these are well known to the mathematicians, and we're going to sort of just borrow these facts and then see what they teach us about the physics. So the mathematicians have classified these eigenfunctions a long time ago, and there are three different types. The first eigenfunction is just a constant function. So this is not a very exciting function, and this is trivially an eigenfunction with eigenvalue 0, because obviously when you take two derivatives on this function, it just vanishes. And this function is also trivially modular invariant. Then there are two types of other eigenfunctions. There's a continuous family, an infinite continuous family, that I'm going to call the Eisenstein series, and I'll define them momentarily. And there's an infinite discrete family. So they're labeled by an integer, 1, 2, 3, 4, called the Moss-Cusp forms. And these will both play an important role. And roughly speaking, the intuition is you can think of these first ones as the plane waves. When you do quantum mechanics, you can these oscillate as you go towards infinity, and these decay. And the second ones are like bound states, so they decay as you go towards infinity. So I think maybe it'll be a little bit more clear if I write out exactly what the definition of these functions are. So the constant is easy. Okay, everyone knows the definition of a constant. The real analytic Eisenstein series are defined as just the modular sum of the imaginary part of tau to the s power, where s is the real parameter we take here. So we take something that's not modular invariant, y to the s, and we sum over all of its SL2z orbits. By definition, once you do the sum, the final answer will be modular invariant because we're summing over the orbit of the group. And for convergence properties, you need the real part of s bigger than 1. But it turns out this can be analytically continued to all s in the complex plane. A simple calculation tells you what this function is, and it admits some Fourier decomposition like this. The actual form won't be important for this talk, but I just want to point out that each of these terms, so there's some Bessel function and square root of y, but each of these terms individually, you can show are eigenfunctions of the Laplacian. So if you take dx squared plus dy squared divided by y squared, each of these terms individually will reproduce yourself up to a factor of s times 1 minus s. So this whole function is an eigenfunction with eigenvalue s times 1 minus s. And each individual term would also be an eigenfunction, but the magic of this particular linear combination of these terms is that this is also modular invariant, which we knew from the definition of the function. So the other thing I want to point out is that this has a scalar piece. So this is like the scalar piece, and this sum is like the spin 1, spin 2, spin 3, etc. piece. So this function has a scalar piece. And the reason I emphasize this is that the next type of eigenfunction is not going to have a scalar piece. So that's one of the classes of eigenfunctions. And the other class of the eigenfunctions are called the cusp forms, or the Moss-Cusp forms. And I denote them by nu sub n. And they take the following functional form. So first, it looks very similar. This Bessel function times square root of y, blah, blah, blah. This is exactly the same functional form as appeared here. There's a cosine 2 pi jx, square root of y, and some Bessel function. And that's because, again, this combination just satisfies, is just the solution of the differential equation you get by demanding that it's an eigenfunction of the Laplacian. But now there's no scalar piece. And so to complete it in a modular invariant way is much more challenging. And it turns out that in order to complete this in a modular invariant way, these coefficients, aj sub n, are going to be some transcendental real numbers. There's going to be no rhyme or reason to them. And I'm going to say a little bit more about these later. But these real numbers are not here to make the function an eigenfunction. They're here to make the function modular invariant. And it turns out that for some, only for a very special values of R sub n, which controls the eigenvalue, does there exist any solutions of these AJs that makes this function a modular invariant, which makes it an eigenfunction of H mod SL2Z. Of course, these A sub j's are only defined up to scale, so I can normalize it any way I want. And I'm going to normalize it so that the first coefficient is 1. This is a little bit of a strange convention because under this normalization, this function does not have unit norm. But as a choice, it's just a normalization, and it's going to turn out to be convenient later. Again, I just want to emphasize that these AJs and RNs are just some sporadic real numbers that you have to solve for numerically. They actually have some very, very interesting statistics, which is very reminiscent of random matrix theory that I'm going to comment on later. But to give you an idea of the first couple of them, here's the first 5 Moss cusp-forms. And the point isn't exactly what the numerical value is, but just to give you an idea of what is going on. So recall the functional equation looks something like this. They're determined by R sub n, which is the index of the Bessel function and controls the eigenvalue of this cusp-form. And then there are an infinite set of real numbers which tell you the weighting of the various different spins that show up in this modular invariant function. So you see for the first one, the first eigenvalue shows up at eigenvalue roughly 190, and you get these random real numbers for the first 4 coefficients, and so on and so forth. These are just random real numbers that there's no closed form expression for them that I know of. They're conjectured to all be transcendental, except the first one, which is of course just a convention. And mathematicians are very interested in these numbers for a variety of reasons, some of which I'll talk about later, and they've computed them to a lot of precision. For example, just for fun, this is a paper that appeared about 15 years ago by Booker, Strombergerson, and Venkatesh, and it's called Effective Computation of Moss cusp-forms. And in the abstract, they say they have computed them to 1,000 decimal places. And they aren't joking. This is a screenshot of one of the supplementary files of their paper. Obviously, this isn't particularly, the details of this don't particularly matter, but I just want to emphasize that these are just really random numbers that are very interesting statistical properties, but there's no nice expression for any individual one of them. So again, so just to recap, what have we discussed? We've discussed the eigenfunctions of this Laplacian equation on H mod SL2Z. And the upshot is that there are 2 different types of eigenfunctions that will form a orthogonal basis. The first is these Eisenstein series, and I'm going to restrict to the principal series. So S is equal to 1/2 plus I times T, where T is a real number. They're defined by this expression right here. There's some known expression. Okay, you can look it up, and you can check that this is modular invariant and that this is an eigenfunction with eigenvalue 1/4 plus S squared. And then there are these. So this is a continuous series because T can take any continuous real value. And then there's an infinite discrete number of cusp forms which don't have a scalar piece, and they have random eigenvalues like 190, 314, 377, et cetera, et cetera. These decay exponentially when you go towards I infinity because of the properties of the Bessel function. And these 2 plus the constant, there's a theorem that tells you that these functions form a basis of all square integrable modular functions. By square integrable, I mean that the square is integrable when you use the appropriate measure. So to put this in a little bit more detail, there's a decomposition, sometimes called the Rolke-Selbrecht decomposition, which is that any square integrable modular function, f of tau, which is, by the way, not holomorphic in general. I suppressed the tau bars just for convention, but this is not a holomorphic function, can be written in terms of the following: a constant, some integral over the Eisenstein series along the line 1/2 plus IT, and then a discrete sum over these random cusp forms which have these sporadic random eigenvalues. The coefficient in front of these is just given by the inner product of the function with the Eisensteins or the functions with the cusp forms, or the functions with the constant. And this division here is just because I've chosen a peculiar normalization for these cusp forms. So just to take a step back and recap, why is this an interesting thing? The goal is to, once you have decomposed a modular invariant function in this form, modular invariance is completely obvious because every single one of your basis vectors is modular invariant. What is not obvious is discreteness and unitarity. So compare this, let's consider the partition function of a conformal field theory. The way that we usually decompose this partition function is we decompose it into representations of the chiral algebra. For example, representations of the Virasoro algebra. So we can take the partition function and write it in terms of the vacuum character squared and various massive representations. In this decomposition, modular invariance is a miracle because each of these individual characters is not modular invariant. However, what is invariant, what is obvious is discreteness and unitarity of the spectrum, because you just take this decomposition and you look at the overlap coefficients and you check that they're positive integers. So each of these, like this number will be like 7 or something, and that's counting the dimension of the Hilbert space where we look at the verbal module where the left moving conformal character has dimension 3.7 and the right moving has dimension 5.7. And we just count those number of states and we always have to get a non-negative integer. Whereas something like this function has the opposite property. Modular invariance is completely obvious when we decompose it in terms of this basis because all of our basis elements themselves are modular invariant. However, discreteness and unitarity are completely obscured in this presentation. And the hope, the sort of big picture of this talk is we're going to hope to use this new decomposition to teach us constraints about conformal field theory in sort of a dual approach. Instead of considering this approach where unitarity is obvious and then we use constraints of modular invariance, we will take this dual picture where modular invariance is obvious and we'll look at constraints of, for example, unitarity. So the big picture question of this talk is, can we use this decomposition to learn something interesting about CFTs? So maybe now is a good place to stop if there are any questions.
I have a question. This sounds similar to. Oh, hi, how are you? It sounds similar to what people do also for the 4-point function.
Absolutely.
Sorry, one second. Sure. Is there an analogy of this function? Like I think they appear from Witten diagrams.
Yeah.
Is there an ADS3 calculation that will give you this? I don't know, maybe it's a stupid question, but
no. This is a very good question. Yeah, absolutely, very good. So indeed, as I should have mentioned, there are a lot of works about decomposing. They're very similar decompositions when you decompose into eigenfunctions, the Laplacian, where you look at 4-point functions, and this is related to something called like conformal partial wave expansion. One thing that's a little bit different is I think that would be more analogous to the following, which would be decomposing in eigen. So let me scroll back up. That would be like decomposing in eigenfunctions of all of H, and there are two parameters: the energy and the spin. So there, J would be a parameter, and also S would be a parameter. And because if you decompose an eigenfunctions of H, modular invariance isn't guaranteed. But what is guaranteed is that you're an eigenfunction of the Laplacian, and then there may be some nice inversion formulas. This is like modding out by the sort of space modded out by the crossing group. And I actually don't know. It could be just my ignorance, but I don't know of a sharp analogy with something done in 4-point functions, and I think it would be interesting to explore that. So, for example, I don't know of an analogous of these cusp forms in this 4-point function case, yeah.
I see.
But it's very related.
Does it help if somehow you think of the torus partition function as some 4-point function in?
Yeah. So good. Yeah, of course. Yeah, good. So I guess you could take like the double cover copy theory, and then you can map it to 4-point function. So maybe that would be like, I think in general, if you just take 4 identical operators and look at this correlation function, then you can write it in terms of some SL2Z. So I think decomposing that in this language might be interesting to see.
Okay, thanks.
Yeah, thanks. Okay, so okay, good. So this is sort of the big picture motivation. Okay, there's okay, good. So the question is, can we apply this decomposition to CFT partition functions? There's actually an immediate problem that we're going to run into, which is part of something that I was sweeping a little bit under the rug. So when I said that all of these functions have this unique decomposition in this form, I said that the function had to be square integrable, like here. The problem is partition functions are not square integrable. They don't obey this equation. So why is that? So what would the conditions be for some function f to be square integrable? The first thing we want to assume is that f has no poles away from the point infinity. That's a very reasonable assumption for a partition function, because that is just the statement that at finite temperature, the partition function never diverges. You don't get some Hagedorn transition. So if you assume this, then the only bad behavior for convergence that you have to worry about is near where y, which is the imaginary part of tau, goes to infinity. And that means that it has to grow smaller than a square root. Right? If it's a square root, you get a logarithmic divergence. So as long as it's sort of, if this function f is less than square root of y at large y, then it's square integrable, and that's sort of an infinitely statement. Whereas partition functions are much, much worse, because there's a Casimir energy when you look at the energy spectrum on the cylinder of minus c/12, which means that the vacuum state and any light operators will be very, very bad. They're not just bigger than a square root, they're like exponential. So they're worse than any polynomial. So partition functions are extremely not in L2. So this theorem that the mathematicians have promised us may not necessarily apply. This is a little bit of a well, this is an important problem. We're going to get around this problem first for a special class of theories as a warm-up, which are these free boson Narayan conformal field theories, and then we'll discuss it with general irrational CFT. By irrational, I mean truly irrational, meaning let's say a finite twist gap. The basic idea of how we're going to get around the problem is the following. There are only a finite number of badly behaved states, which are the states that are quote unquote sufficiently light. These light operators are the ones that give you this exponential divergence. So we're going to remove them in a modular invariant way. And once we remove them in a controlled way, then we're going to be able to do the spectral decomposition. So let's as warm up, let's first study these Narayan CFTs. And these Narayan theories are quite interesting for a number of reasons. First of all, they're free theories, they're exactly solvable, but recently there were some proposed holographic dualities of averages of Narayan theories with some bulk exotic theory of gravity in 3 dimensions. So I'll also comment a little bit about that. So that's sort of, in addition to an interesting warm-up, it's a good, I think, motivation for studying these theories. So first, let's consider the simplest theory that we can think of, which is the C=1 free boson. This is a free theory. We could just write the action. We have some field x, which we demand that it's periodic under a shift of the radius. There's some convention of 2 pi's. And the action is just this free action here. So you can just exactly solve this theory, and it's done in like chapter 2 of Polchinski. And you can write down the spectrum, the partition function of this theory. So here I'm going to label it by the modular parameter tau and the radius r, which is the periodicity condition of this circle, the radius of this circle. And the spectrum is very simple. It's first given by this function 1/eta squared, which is defined here. And what this is actually like this Ramanujan counting function. And what this is this is just counting the oscillators that you get by acting by in the free boson oscillator modes. So you can add this alpha -1, alpha -2, et cetera, and this is just a generating function for counting that. However, that's not the full partition function, because there are also non-trivial winding and momentum states for, you can think of it as like a string wrapping the circle or having a finite unit of quantized momentum along the circle. And if you work out carefully the energy spectrum and the momentum spectrum of that, you get the following sort of lattice theta function. So we sum over all integers n and w. W counts the wrapping number and n counts the momentum number. And you get some energy, which looks like this when you work it out. So, okay, the details don't really matter. The only point is that there exists some closed expression here. Okay, I'm also going to very quickly introduce a very simple generalization. Instead of 1 free boson, we can consider C free bosons on a torus, TC, and we can write a general action like this. So this looks very complicated, but it's not. Now, instead of having dx d bar x, we're just going to have, first of all, we're going to have C different scalars. So this index P and Q runs from 1 through C, and they just label the different scalars that we have. And this GPQ, from the point of view of this worldsheet 2D theory, is just a space of coupling constants. It's just some C by C symmetric matrix. And this alpha beta are the 2-dimensional worldsheet indices. And we can also have an anti-symmetric a term, which we call BPQ. So these words G and B in string theory have some interesting interpretation from the space-time, but if you're a two-dimensional person, these are just some coupling constants that tell you which conformal field theory you're describing. So for us, these will just be some random coupling constants, which are described by C symmetric and antisymmetric matrices. And this is still a free theory. You have to work a little bit harder to get the spectrum, but you can do it. It's done in various textbooks. And I'll just write down the answer, but the details don't matter. But the point is just that, again, you get these oscillator modes here. And then you get, again, this sort of generalized momentum and winding lattice sum. And there's some energy, which is known, and then there's some spin. You can check that this partition function, although it's not at all obvious from the way it's written here, it is modular invariant. And it is, of course, manifestly unitary and discrete, because you can just do the expansion and you'll see positive integer degeneracies. So it's modular invariant, which means it has an SL2Z symmetry acting on the world sheet. And actually, if you take these matrices G and B, there's actually an interesting discrete group, which is called OCCZ, which can act on it. And this is a symmetry called T-duality. So what this is roughly exchanging these momentum and winding vectors into themselves. So the simplest version of this is in the C=1 free boson. There's a symmetry where I take R to 1 over R, the radius to 1 over the radius. And the units work out with alpha prime, the tension of the string. And there's similarly some interesting discrete symmetry for the target space here. And this will be, it's not going to be crucial to the talk, but I only point this out because it'll make some interesting connection to this harmonic analysis. So instead of decomposing the partition function, so now this partition function again has a Casimir energy. So if we were to try to decompose the partition function, we would run into the problem that I said earlier, which is that the function is very much not square integrable. It diverges exponentially when you look at the near the cusp. What we're going to do is instead we're going to look at the only moduli dependent piece. So we're going to take out all of the oscillators and just decompose the lattice theta function. The lattice theta function was just this piece right here. Now you might object and say this isn't modular invariant, and you're right, because to get this piece we had to take out the oscillator modes. But the oscillator modes have a well-known transformation property under modular invariance, and in particular they pick up a weight. And that can be just soaked up by a power of y to the c over 2. So the upshot is, I'll just tell you the following fact, which is you can basically change coordinates to rewrite the partition function in a way that's modular invariant, and now doesn't grow exponentially at the cusp, but rather grows polynomially. Now polynomial is still too fast, it's still bigger than square root of y, but it turns out it's much, much better, and polynomially we can handle. What we're going to do is we're going to subtract out a term that grows as y to the c over 2 to get something that's square integrable. In particular, the thing that we're going to subtract out is the average partition function of the free boson. This was computed in a series of papers from about 1 year ago that I'll review momentarily. And it has a function. It's a function with a name. It's in fact another one of these Eisenstein series. But the point I want to emphasize is the following, which is that what we're going to be decomposing is the lattice theta function deviations from the average, and that was always going to be square integrable. So let me just say this again. The average over the target space of C-free bosons was recently considered in some toy model of averaged ADS3 CFT2. So this was motivated by these beautiful works on relating JT gravity to averaging averages, including averages of SYK theories and random matrix theories, and trying to move it to one higher dimension. And it was shown by these two series of papers that the average of C-free bosons is given by some function called an Eisenstein series with S equals C over 2. So earlier I defined this for all S, so you can take S equals C over 2. And this is a modular sum of the SL2Z matrix acting on Y to the C over 2. And in these papers, they conjectured or interpreted this modular sum as a sum over different bulk geometries in the ADS3. So they took this as a sum over classical geometries weighted by some Chern-Simons action. Okay, the details of that is interesting motivation, but for a technical purpose, what we just need is that this has the same growth rate that we need to subtract off to make our final lattice theta function square integrable. So the point is we're going to compute the spectral decomposition of the deviations of the average partition function, of the partition function from the average. Okay, any questions? So let's do this explicitly for 2 examples. So here the formulas will get a little bit hairy, but the details don't matter. I just want to give you a flavor of what the computations will look like, and then it'll be clear what the structure is at general central charge C. Actually, C equals 1 and C equals 2 are also rather special because there the average diverges for both of them. They have to be defined via analytic continuation, and the analytic continuation of this average has a 0 at C equals 1 and a pole at C equals 2. So the average, strictly speaking, is only well defined for C bigger than 2, but our spectral decomposition will work for all C. So to do C equals 1, we subtract out the average, but the average when analytically continued is 0. So we don't have to subtract anything to do the average. So we simply need to compute the following 3 integrals. We need to do the overlap, this Peterson overlap integral with the constant, the Eisenstein series, and the cusp forms. These are just 3 integrals, and there's some techniques you can use to do them. I won't go through this in detail. I'll just tell you in words. There's a very beautiful trick to compute these integrals called the Rankin-Selberg transform. And the idea is that if you can write some integrand as a sum over SL2Z, and you're integrating over the fundamental domain of some sum over SL2Z, then you can basically move this sum. You can move this sum past the integral and have and then consider the integral over the entire upper half plane instead of just over the fundamental domain of the original function f times the original function g. And technically, this integral can be much, much easier because you don't have to deal with this weird, the weird shape. You're just integrating over a rectangle, basically. It'll essentially just reduce to a Mellin transform. So if anyone is interested, I'm happy to talk about this trick in more detail. But just sort of very quickly, it turns out we can rewrite the theta functions to look like a sum over SL2Z, and it allows us to do the integrals. So I'm just going to tell you what the answers are. This is what you get when you integrate it against the C equals 1 partition function at radius r against the constant. This is what you get when you integrate it against an Eisenstein series. And you get 0 when you integrate it against the cusp forms. So that means that we have the full spectral decomposition of the C equals 1 lattice theta function. And it's given by r plus r inverse times some integral of the Eisenstein series times this function of r. This is manifestly modular invariant because we're decomposing it into modular invariant functions. I also want to point out that it's also manifestly T-duality invariant. Recall that T-duality will take the radius to 1 over the radius. And we see here that this term is obviously invariant under T-duality, and this term is also obviously invariant under T-duality. It's not going to be a coincidence that the T-duality popped up. And let's see why. So let's study the interpretation of these overlap functions. Okay, so here's the function again, which I just rewrote just for convenience. So we've decomposed it into eigenfunctions of the Laplacian on the worldsheet moduli space. So recall that's just these Eisenstein series here. It turns out that the other functions are going to be interpreted as eigenfunctions of the target space moduli space. So recall that at C equals 1, the target space is labeled by the parameter r, and this has a Zamolodchikov metric, which is given by dr squared over r squared. This is given by just the 2-point function of the marginal operator. And from this metric, you can compute a Laplacian. Okay, it's given here. And this Laplacian has the following eigenfunctions with the following eigenvalue. This, you'll notice, is precisely this. And so what we've done is we've decomposed the partition function into correlated eigenfunctions of the target space and of the worldsheet Laplacians. Okay, why was this a natural thing to expect? So here's a fact that I'm going to tell you that's very, very easy to prove, which is Narayan partition functions all satisfy the following differential equation. If you take the Laplacian of the worldsheet and the Laplacian of the target space acting on these theta functions, they're going to be the same thing up to a constant. The intuition of this is very simple, which is that the Laplacian of the worldsheet is like you changed your modular parameter tau. So roughly speaking, it's pulling down some factors of the stress tensor T. The Laplacian on the target space is like a derivative moving you in the target space, which means you're moving in the marginal operator. But the marginal operator is just j squared. So this is roughly pulling down factors of T, and this is pulling down factors of j squared. And Narayan theories, the stress tensors are pure Sugawara, which means that they're roughly the same thing. So that the Laplacian on the worldsheet and target should be intimately related. And if you work out the details, it's related by this equation. You'll notice that, for example, if I plug in C equals 1, this number is 1/4. And indeed, the eigenfunction here is s times 1 minus s, and the eigenfunction here is s minus a half squared, and those are differ by precisely 1/4. Okay, so let's see how this works at c equals 2. So at c equals 2, the moduli space is 2 by 2 symmetric and antisymmetric matrices with some t duality. And it turns out that there's this accidental isomorphism, and this is given by 2 copies of the fundamental domain H mod SL2Z. This actually makes sense. The reason, what these 2 moduli are just the complex structure modulus of the torus and the Kähler modulus of the torus when you appropriately complexify the Kähler modulus. So if you take the metric, you can write these coordinates rho and sigma here, and T duality acts by 2 independent modular transformations on this rho and sigma. So you can read it. This was first discovered, I think, by Dijkgraaf, Verlinde, and Verlinde. So the partition function at c equals 2 will depend on 3 parameters: the modular parameter tau and two target space parameters rho and sigma that are also each have an SL2Z action acting on them. The SL2Z is very different. This is the modular invariance, and these 2 SL2Zs are the T duality. So remarkably, though, even though these coordinates have different original meaning, there's actually a triality where you could permute any of these 3 coordinates and the partition function remains the same. And although you can prove it rather simply, I think that the mystery, the reason why there's this triality is very mysterious. So exchanging rho and sigma is just a special case of mirror symmetry, but exchanging the world sheet and target coordinate, I think is still rather mysterious. Okay, so again, we can compute do the spectral decomposition of central charge c equals 2 using the same trick. Now, again, before we do the calculation, let's try to guess what the answer would look like. So recall, we always need to subtract out the average partition function EC over 2, because we're computing deviations from the average. Unfortunately, here's a technical point. At c equals 2, this function diverges. However, there's a regulated version, which I call E1 hat, which is defined as just the limit as s goes to 1 of E sub s minus 1 over s minus 1. This turns out has the right growth properties such that if I subtract it, my partition function is still an L2. So this is going to take the proxy of our average. This is just an accident of c equals 2. Finally, we need to obey the differential equation and the triality conditions. Now, the eigenfunctions of the target space are very simple to state because the target space Laplacian is just 2 copies of the same Laplacian of the worldsheet space. So therefore, the eigenfunctions are just products of eigenfunctions of the worldsheet. So I'll just flash the answer now, and then we'll go through it a little bit slowly. So this is the final answer for the c equals 2 partition function as a function of the worldsheet parameter tau and the 2 target space parameters rho and sigma. Okay, so let's unpack this for a little bit. Alpha is just a constant. Okay, whatever. Let's not worry about this constant alpha. This E1 hat of tau is what we subtracted off in order to make the answer square integrable. So if we move this to the left-hand side, then we'll get something that's square integrable. And the mathematicians have promised us that we can write that in terms of a constant E sub s of tau and nu n of tau. And that's precisely what we have here. This term is the constant. And you'll notice that it has to be E1 hat of rho plus E1 hat of sigma in order to obey the triality, this triality condition of these 3 moduli. Similarly here, this whole term here is interpreted as the overlap for taking the c equals 2 partition function against the Eisensteins. However, it takes a very constrained form. It has to be 2 copies of the same eigenfunctions as ES of tau in order to obey the triality and the differential equation that we wrote earlier. And this is just some convention, essentially. And finally, there are the cusp forms, where again, these cusp forms, which I remind you, these were these random functions that the mathematicians computed to 1,000 decimal places, or like the Fourier coefficients were these like random transcendental numbers, and they had no rhyme or reasons. And again, they have to appear in triplets in order to obey the triality and this differential equation here. And the coefficient, and there can be a coefficient in front that depends on n. Remarkably, the coefficient for all of them is the number 8. I think this is really, really miraculous because this c equals 2 partition function is some CFT, it's some discrete unitary spectrum. And when we decompose it into these cusp forms, there should be nothing nice that we expect about the coefficient we get. Because remember, each of these guys was defined as some eigenvalue with some horrible transcendental number and yada, yada, yada. And if this 8 were some totally random number, different for every value of n, we would still obey the triality condition, and the correlated eigenfunctions. But somehow, miraculously, we get the same number for all of them. And I think it would be really wonderful if this 8 were something physical that we're counting. I don't know what it is, but I think it would be interesting to explore a little bit more. Okay, so now that we've warmed up with C equals 1 and C equals 2, let me say what the general C answer is to sort of bring it all together. So with C equals 1 and C equals 2, where we write in terms of eigenfunctions of the Laplacian of worldsheet and target space, we'll have to do this for general C. We actually, unfortunately, I don't know in the math literature if they've computed a closed form expressions for the target space eigenfunctions. But in terms of them, the final answer is this expression here. And it looks a little bit complicated, but let me just say what each individual term is. So here is the average over target space moduli space. This is what we subtract in order to make the function square integrable. There's similarly an average over the worldsheet moduli space. This was the analog of these two terms in C equals 2. Actually, these have been computed before in a series of very beautiful papers by these people and others. And the reason is that averaging over worldsheet is a very natural thing to do in the context of string theory. So that was their motivation, and many of the similar calculational tricks have shown up there. Finally, there'll be two infinite terms. One, there'll be a continuous eigenfunctions of the worldsheet and continuous eigenfunctions of the target space. And the eigenvalues of these continuous eigenfunctions will be correlated in precisely the way that this differential equation that I showed earlier demands. And finally, there'll be an infinite set of sporadic discrete worldsheet eigenfunctions and an infinite set of sporadic discrete target space eigenfunctions, again with eigenvalues correlated in this way. Interestingly enough, this makes sort of a mathematical prediction, which is that this space, whatever its discrete eigenfunctions are, there must be like their eigenvalues must be like precisely correlated with these cusp form eigenvalues. They just have to be the same up to a shift of C over 2 times 1 minus C over 2. In this decomposition, by the way, the statement of these two papers that the average free boson partition function is simply this function right here becomes obvious, because whenever you average a single Eisenstein series, it vanishes over the target space. So this integral vanishes. Whenever you average this over the target space moduli, which I called M, this also vanishes. And finally here, when you average this function over the moduli space M, this also vanishes. So the average over target space is just given by this term right here. This is the only one that survives. Similarly for the average over the worldsheet. Okay, I think I'm supposed to stop after 50 minutes, so maybe I'll just say this very quickly, which is that with this decomposition, there are various interesting properties of the CFT that you might be interested in. For example, you might be interested in the gap of the spectrum. With this decomposition that I've written down, it's very easy to read off the scalar gap of the spectrum. By scalar gap, I just mean the lightest non-vacuum scalar operator under the maximal chiral algebra. So there are various interesting behaviors that this can have. And this can be a proxy to study black holes, because this is sort of like, you can think of it as the lightest non-spinning black hole in this theory. And you can ask, what is the scalar gap as a function of the target space moduli, and can you extremize it? So if you can extremize it, that would be a theory that's sort of kind of a very gravitational theory, because there are no light degrees of freedom. And it was shown that in some recent work that the average scalar gap obeys certain properties at large C. And with this technology, I believe it can be, one can read off the, in principle, one can read off explicitly the scalar gap as a function of all moduli. In practice, we're only able to do it at C equals 1 and C equals 2 so far, simply because we don't have explicit expressions for these target space eigenfunctions. But that's simply a mathematical, if some mathematician works out the harmonic analysis of this space, then it'll be very easy to read off the gap. Well, if people are, I can describe this in a little bit more detail. The idea is you just take the scalar spectrum and you integrate from 0 to some value delta. And if delta is smaller than the gap, then this function must vanish, right? Because by definition, if all of the states are above some delta gap, that means that this integral will equal precisely 0. And from this Fourier expansion of the Eisenstein series, you can get a very explicit expression for this counting function. And then you can deform, you can do some contour manipulations, and you can show that the gap will be given precisely by, will be controlled precisely by the growth of this overlap function right here. So the analytic properties of this overlap function of the partition function with the Eisenstein series secretly encode what the scalar gap is. In particular, if you work out the details, it turns out that this FC of S, which is the overlap of the partition function with the Eisenstein series, multiplied by some prefactors, has to scale as the gap to twice the gap to the negative S. So let me just give an example to say what this is. At C equals 1 T duality invariant coordinate for the moduli space is radii from 1 to infinity, right? Because R goes to 1 over R, you can make R bigger than or equal to 1. And this function here at large S scales as R to the 2S. That means that the gap is 1 over 2R squared. And this is minimized at R equals 1, which is the self-dual point. So this spectral decomposition then we derive the well-known fact that the self-dual point has the largest oh, sorry, this should say maximized, has the largest scalar gap. Similarly, at C equals 2, if we choose rho and sigma to be in the usual fundamental domain, then this term here grows as rho 2 times sigma 2, the imaginary part of rho times the imaginary part of sigma to the S power. And that means that using this formula for the gap is 1 over twice the imaginary part of rho times the imaginary part of sigma. And if you want to, this is again typo, this is maximize. If you want to maximize this gap, you simply need to minimize the imaginary part of rho and the imaginary part of sigma. Well, we can just look at this picture right here. That's minimized at this point right here, the Z3 symmetric point, which is a value of square root of 3 over 2. So if you plug in square root of 3 over 2 for both rho 2 and sigma 2, you get a gap of 2/3, which is the maximum gap possible for a C equals 2 Narayan theory. And I think it would be interesting to understand harmonic analysis of OC, C well enough to be able to say, hopefully, analytically, what the gap is as a function of all C. I don't know if that's possible or not, but I think that's a possible avenue. Okay. Yeah, are there any questions on this, on the Narayan examples? Okay. So far we've been studying a spectral decomposition of these Narayan theories, which are a very special class of theories. What about a generic CFT with only Virasoro symmetry? So here now we can't take out all these U1 to the C different descendants. We can only take out the Virasoro. So let's define the primary partition function where we just take out the Virasoro descendants. And now this goes as, this still is exponentially divergent, which is a badly divergent exponential. And in particular, in general, primary operators with some dimension delta in spin J will contribute as the following to the primary counting partition function. So somehow we need to remove all operators with total conformal dimension less than or equal to C minus 1 over 12 in a modular invariant way to make the function square integrable. So here's some of a picture here. Somehow we need to remove all operators in this triangle region here in order to make the function square integrable. These operators are very dangerous and they grow too quickly. Fortunately, there is a well-known prescription of how to do this. There's a well-known prescription to subtract such operators in a modular invariant fashion. What we do is we take any such badly behaved operator here, and we do their SL2Z sum. And this will give a spectrum that looks like the following. Here's your input operator, and here are your output operators. And all of your output operators outside of this danger zone. And you can read these papers here to see the details of this construction. So what we do is we subtract out the Poincare sum of finitely many operators with total conformal dimension less than C minus 1 over 12, and that will give a square integrable function. This is precisely what we did in the Narayan case. There, the analog of the C minus 1 over 12 is 0 because the number of currents was simply given by C. And so the only thing we needed to subtract off was the vacuum state. That had delta equals 0, and that was the vacuum operator. And there, it had an interpretation as the average, and the rest was square integrable. So we subtracted off this term here. We got the rest to be a square integrable function, and then we used our technology. It would be extremely interesting if, in general, this Poincare sum of the light operators had some interpretation as an average of theories. It's not clear what you're averaging over because these theories, in general, don't have moduli. And moreover, you have to be a little bit careful to make sure that the average is positive definite. In my remaining couple of minutes, let me just say some interesting applications that we can do for 2D CFTs in general. So with this technology, we can prove a new theorem about what I like to call spectral determinacy. So here's the theorem. We can show that the entire spectrum of a two-dimensional conformal field theory is uniquely fixed by all primary operators that are light, meaning their total dimension is less than c-1/12, all scalar primaries, and all spin 1 primaries. Well, actually, I could change spin 1 to any spin j. So here's a picture in some like a Chew-Frouchy type plot. On the x-axis, I plot the total conformal dimension, and the y-axis, I plot the spin. And there's a unitarity bound. Everything must fly below this line right here. If you tell me all operators in this triangle regime and all operators of spin 0 and spin 1, the remaining operators, their conformal weights and degeneracies are uniquely determined. You can't mess with them. And the proof is very simple. So let's suppose otherwise. Let's suppose there were two partition functions that agreed in all the blue regions above. We could take their difference, and their difference would be square integrable, which by definition means it can be written in terms of this basis that we've been considering. And it turns out that the scalar part alone is enough to determine the overlap with the continuous series. And if the scalar part vanishes, the overlap is 0. And then the spin 1 part is enough to determine the overlap with the discrete series, and the overlap would be 0 as well. So therefore, the difference would vanish, and then these two spectra would be identical. I personally believe this bound can be improved if one introduces notions of discreteness. I'm very happy to discuss this more in the discussion session, but I think if you impose that the inverse Laplace transform must be a sum of discrete delta functions, it's possible that you could get rid of some of these constraints and determine the entire spectrum from even less data. And also this might constrain theories of pure quantum gravity under some definition of pure. Okay, I think I'm a little bit out of time, so let me just take one more minute or so and discuss possible future directions, and then I'll end and take questions. So I think some interesting directions are the following. I think it would be very interesting to use this new technology to try to bound gaps as a function of the central charge, either for Narayan theories as a warm-up or for the more interesting Virasoro case. One thing that would maybe interesting is try to use leverage discreteness in the CFT spectrum, because most combinations of these basis vectors will not lead to a discrete spectrum. So there's something very, very special about the combination of the basis vectors that leads to discreteness and positive degeneracies. It would be interesting to use this spectral decomposition to compute powers of the Narayan ensemble. This was recently some very toy version of SYK was considered recently by these authors, and they found some interesting additional saddles which resolve some factorization puzzles. And it would be interesting if there's an analog of that for the Narayan case. This question I asked, is there any interpretation of averaging in the Virasoro case? I think I've gone over time. I'll stop here and take questions. So thank you very much for your attention.
Thank you very much, Nathan, for your nice presentation. Any questions or comments? No questions or comments. Actually, the first paragraph that you showed reminds me of the brilliant zones in the condensed matter physics, but that's a different topic, of course. Mm-hmm. But I just it reminds me of that because I've seen that in many textbooks of condensed matter physics because of the periodicity there. Okay.
Yeah, that's an interesting comment. Yeah, I don't have to say, but yeah. Thanks for that comment.
So in that case, if we have no comments or questions, then we conclude our session for today. We are going to meet again tomorrow at around 3 o'clock GMT time. So till that time, so have a nice day, and see all of you tomorrow.